Last time I have written down some kind of a relationship between the matrix elements of a representation. So let's just remember this. So this is called the orthogonality of matrix elements. Okay, so that's basically a sum over the group elements times u of IP for the mute representation, IP matrix element, complex conjugate, and for the mute representation, JQ matrix elements multiplied together for the same group element, and then there's a sum over group elements, right? And then we have said that this is equal to G divided by D. D mu is the representation dimension, and then we have these three delta functions, right? I basically said that, I mean, this three delta function essentially says that these three indices are equal to the corresponding indices in here, right? In any case, usually there's this group order in here that appears. We can move it to the left-hand side. People usually do this. So as a result, we have 1 over d mu in here, and then 1 over the order of the group. So as a result, the left-hand side looks like an average over the a group or something like that. Okay. So in any case, I was actually going to demonstrate this on a group. And then we have said that, well, because of this, we had these, like we have defined these W mu IP vector. Oh, right, let me write it down. W mu IP vector, we have defined it like this. Its G component is defined as the square root of the dimension divided by the group order multiplied with the this element, the matrix element. So basically, for every representation and matrix element, we just define this. This then gives us some kind of a vector. And then we have said that this W mu IP is an orthonormal set. I can just show that it's an orthonormal set. But later, I have said that we are going to show that this is actually an orthonormal basis because the number of vectors is basically equal to the order of the group. And then whatever, so from here, we then deduce that the sum of the dimensions squared is less than or equal to the order of the group. In any case, I'm just going to talk about this group S3, right? So group S3, okay? So in that case, it appears that there are three irreducible representations, well, three inequivalent ones, right? And it appears that the first two ones have the dimensions 1, and the last one has dimension 2. So as a result, the sum of these dimension squared, d2 squared plus d3 squared. So let me write it down like that. So the sum of the squares of the dimensions is equal to 6, which is the same thing as the order of the group, right? This is the symmetric groups, the permutations of three objects. Let's just remember this. So as a result, then the representations that we have already found must be all of the irreducible representations of that group, right? So as a result, I'm just going to prepare this table in here. This table shows the representations, right? So I'm here writing down the matrices in here. So that's the first representation. And this is the second one and the third one. Here I'm writing down the matrices for each representation. So the first and the second row are actually 1 by 1 matrices. You can think of it like that, but usually you don't make a distinction between a 1 by 1 matrix and a number. So the first irreducible representation, I mean, all one-dimensional representations are irreducible in any case. The first one is the trivial one. So let me actually right, somewhere in here. So, okay, this is the trivial one. It's the representation that every group has. It's one irreducible representation that every group has. The second one is called the signature. We have also talked about this thing before. How did we talk about? Well, we talked about the signature of a permutation, whether it's an even permutation or odd permutation. Let's just remember, these are all transpositions, so transpositions are always odd. And these are three cycles. We have said that a three cycle can be written as a product of two transpositions. So these are all even, right? So the even permutations have signature 1, and the odd permutations have signature -1. So it appears that in the symmetric group S3 or S4 or S5 or whatever, there are only two one-dimensional irreducible representations, and these are those ones, okay? And we don't have any more in all of the other groups. And well, this has some, I mean, this basically permutation symmetry is actually something that we need in quantum mechanics for the case of identical particles. So for treating the symmetry of this identicalness of the particles, we use this group. And it appears that this particular representation, the trivial representation, is the one that appears for bosons. And this is the representation that we actually need when we are discussing fermions. So as a result, these two special representations have these special places in physics, right? In any case, all of the other representations are higher dimensional, like this one in here. So all of them are higher dimensional. Let me clarify my thoughts in here. So from time to time, they also appear in physical expressions, especially when you have like, I mean, for identical particles, sometimes people need to separate the space part and the spin part. And for these kind of things, these higher dimensional representations appear to be useful, all right? I'm just going to mention it in here. But apart from that, we don't have this. So in any case, so I'm just going to describe this procedure in here. And I don't know if it is useful or not. So what I do is I just take all of these matrix elements, and if I basically multiply it with the square root of this dimension divided by the order of the group. So as a result, I'm going to start with this one. It's basically this matrix element. So as a result, the first vector that I'm going to write, again, this is a vector that I just write down for the purposes of the discussion that I do in here, right? So in any case, it doesn't appear anywhere else. So in any case, what we do is for the first representation, and that's the 1, 1 matrix element, I just list all of these numbers, all right, in a column vector of dimension 6. Sorry about this. Right? This is a 6-dimensional column vector. So that's my first vector. You can see that it is normalized. The second vector is basically the representation 2 and these matrix elements. Obviously, there is only one matrix element. So I'm going to call this as W211. So that's also 1 over root 6. 1, -1, -1, -1, 1, 1. You can also easily see that this is normalized and it is orthogonal to the first one. Now I pass to this representation and this matrix element. So what I do is I just write down these entries in here, right? Just keep this in mind, all of these 6 entries. But since I'm just going to undo these, I'll just list these in a vector. There's also a coefficient in front. So that's W311. The coefficient is square root of 2 over 6, but I'm going to simplify it as 1 over square root of 3, all right? And the coefficients are 1, minus 1, 1 over 2, 1 over 2, minus 1 over 2, minus 1 over 2. Again, you can easily check that this is normalized. Please do so. You can easily do this kind of calculations. In any case, I'm going to continue. This time I'm going to pass to 3, 1, 2. So that's basically, let me write this coefficient in front. Which elements I write in here? So these are the 1, 2 matrix elements of these matrices. Right? It's all of these 6 ones. So let me quickly do these as well. So that's 0, 0, minus root 3 over 2, root 3 over 2, minus root 3 over 2, and root 3 over 2. Yeah, I mean, we could simplify these actually. So let me quickly write down the last two. So that's W321. That's 1 over root 3 again. So this is 0, 0, minus root 3 over 2, root 3 over 2, root 3 over 2, minus root 3 over 2. Basically, it is these elements. And finally, this is W322. So I think I'm going to start with 1, 1, and then minus 1 half, minus 1 half, minus 1 half, minus 1 half. All right. There's also 1 over root 3 in front. So I think I'm going to write it down like that. Okay. All right. So as a result, yeah, I mean, first the counting. So you can see that there are actually, for each group element, there are 6 numbers in here, right? So the first result that we have shown in here, well, these 6 numbers is basically the sum of the dimensions squared, because we have like, this is 2 by 2 matrix, so therefore there are 4 numbers in here. So that's what happens in here. So the first relation that we have deduced is that the sum of these, sorry, the number of these entries, which is basically the number of these vectors, cannot be bigger than the order of the group. Later, we are going to show that they are equal all the time. This is a case where they are also equal, right? So there are 6 vectors in here, and these are 6 by 1 column vectors. So therefore, this is an orthonormal basis. So W mu IP is an orthonormal basis. Okay. So I think I'm going to do one thing unusual in here. So let me, I mean, this is one way of actually, another way of looking at these relationships. If it's an orthonormal basis, then I construct this matrix. So let me call this as the W matrix. It's the matrix that that's formed when I write down all of these vectors as columns of some square matrix, right? So in any case, there are these 6 columns in here. So just write this thing down. So the fact that this is orthonormal is the same thing as this W is unitary. Sorry, this is unitary. Okay, so we have seen that a matrix is unitary if all of its column vectors is actually, sorry about that. A matrix is unitary if all of the column vectors, all of the columns of that matrix is an orthonormal basis, right? That's what I'm using in here. And then I have said that a matrix is unitary if all the rows form an orthonormal basis. So let me write this thing down like that. So all the rows form an orthonormal basis. So these two statements are basically essentially the same. But interestingly, I mean, you can find another relationship between these matrix elements, provided that this is an orthonormal basis, right? I'm just going to write this thing down. But in any case, let's say that, I mean, this is called the completeness relationship. Sorry about this. It's just the opposite. So this is called the orthogonality of matrix elements. These relations are called the completeness of the matrix elements. Okay, why do we say completeness? Because you can only state this if this is actually a complete orthonormal basis. Okay, only in that case, but I said that we are going to prove that this is the case later. All right, so as a result, I'm just going to write down another form of relationship between the matrix elements, but this would correspond to the orthogonality of the rows of that matrix in here. But I'm just going to express it in terms of the matrix elements, all right? So as a result, I'm going to go back to this relationship. So that's the orthogonality of the matrix elements. So what I do is this. I first of all write down this matrix element in here, IP, G. Take the complex conjugate, write another same matrix element of another, this time another group element, multiply with d mu and divide by the order, and then sum over of all mu I and p. And the result should be equal to delta GH. So that's called the completeness.
Can this be shown alternatively by using the this sum of the direct products of these omega vectors by itself, and their summation is equal to identity?
What is omega? W.
W, yeah, sorry, my bad.
Yeah. I mean, this
identity
corresponds
matrix,
to, yeah. This corresponds to W dagger W is equal to being identity. This corresponds to W dagger being identity.
Yeah,
so
okay.
They express the same thing, but in a different way. Yes. So the answer is yes.
Okay, thank you.
Well, does this give us anything new in here? Well, it isn't really. I'm just going to, I don't know. I mean, we can work this out, but we don't get anything rich in here, right? Unfortunately, right? So as a result, let me actually kind of show it like this. So the summation over IP basically corresponds to a trace. So let me write it down like that. So that's the trace of U mu of G dagger, U mu of H in here. That has to be equal to delta GH. And this is basically, this part is it. You can actually show that this is the case. So that's the representation matrix for G inverse H and whatever. So we basically express some kind of a relationship in terms of the characters and whatever. So let me say that this is useless right now. It will also be useless later because we are going to derive something more powerful. Okay. So I'm just stating this in here as some kind of a, some kind of a mathematical tool that we can use to express the same relationship in a different way. So here I'm summing over the group elements. Here, though, I'm summing over the representations and the matrix elements, right? But somehow these two capture the same thing. Okay, let's go back to characters. character of a representation. So the character is just a number. It's basically, I'm just going to write this thing down. Right? That's the trace of the representation matrix. All right, so let's remember this. So if, let's say, if two representations are the same, if A is equivalent to B, then the character for A and the character for B are the same for all G. Basically, equivalent representations have the same character, so that's why it was important. Another thing is, like, let's say it like this: if A is equivalent to B plus C plus dot 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 D, then we say that the character for A is just obtained by summing for the characters of the other representation. So for the direct sum, we had these relationships. For the direct product as well, but right now we don't need this. So, but these are the things that we are going to use. And then the character of identity is equal to the dimension of the representation. Okay. And then finally, there was this thing. So if G is conjugate to H, so that's the conjugacy relationship in the group. Then we have said that the conjugate elements have the same character. So therefore, the character is basically a property of the conjugacy class. All right, let me write this thing down like that. Is a property of the conjugacy class. Sorry about this, conjugacy class. So it has the same value for all members of the same conjugacy class. So at some point, I'm just going to use this fact, but right now I don't need this. I'm just going to show this. So for irreducible representations, I'm just going to use this notation for expressing the characters, right? Let's say it like this. So this is for the muth irreducible representation. So I'm going to use this notation. So it's always a superscript mu with a parenthesis, right? It's just a strange notation that I'm using. Okay, so let's then go back to this group again. I think what I'm going to do is this. So for one-dimensional representations, the character is basically the same as the representation itself. So that's also the same thing as the character, right? For two and higher dimensional representations, of course, we need to add up all of the matrix entries. So as a result, we have this. I mean, this is a character too. Identity should have a character which is equal to the dimension. This is a character 0, and these two as well. So all of the two cycles in here, which are conjugate to each other, they have the same character, which is 0. And these two have characters -1. Okay, so let's just remember. So using this, we actually do construct what we call as a character table. This is more or less the thing. So first, let me just do it in the long way, right? So there's 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. So these are all conjugate to each other. Sorry, these are all conjugate. These two are also conjugate. Just remember that in symmetric group, two permutations are conjugate if they have the same cycle structure. So the identity is always conjugate to itself. And then we have these three representations. Okay, so for trivial representation, the character is always equal to 1. For the signature, of course, we know what the character is. And for this two-dimensional representation, the characters are basically 2, 0, and -1. Okay, so the important point in here is that since these are all the same, we basically write down the class in here. So let's say it like this. I'm going to call the conjugacy classes classes as CI. So as a result, C1 would be only the identity. The second conjugacy class in here is these 2 cycles. So that's 1, 3, 2, 3. And C3 would be 1, 2, 3, 1, 3, 2. Okay. So I'm also going to call the number of elements, number of group elements within each conjugacy class. So that's going to be important as well. So we have 3 transpositions and 3 cycles, right? So let's say it like this. Ni is the number of elements in class CI, right? I'm also going to call chi I. Yeah, let's say it like this. Chi I as the character of G, let's say for any G in that conjugacy class, right? So since basically the character is a property of the conjugacy class and not the elements, let's say it like this. So as a result, I'm going to use this kind of a notation. So chi mu I, for example, I'm going to use the same kind of a notation, right? So as a result, what we do is, I mean, this is not actually what we call as the character table. The character table is basically this table, right? This is the actual character table. So we have the first conjugacy class identity. Let's say it like this. This is the second and that's the third. So I'm also going to write down the numbers in here. And 3 is equal to 2, sorry. And now I just write down the representations in here. And quickly write these things down. All right, there are several websites for applications of group theory where you can find these character tables for all of the physically relevant symmetry groups. I mean, the physically relevant ones are like the cyclic group, for example, or the dihedral group, or I don't know, the symmetry group of a cube, for example, and things like that. The symmetries that we actually meet in nature in practice, that things like, I don't know, the cyclic group of order 7, let's say, they don't really appear in any applications. I don't think so. So as a result, you're not going to find these. But what you're going to find in there is this character table. Okay, so in the columns, we always have the conjugacy classes within the group. And in the rows, we always have these representations. They usually name the representation with some specific letters, like, for example, E, A, and I don't know, S, and things like that. Okay. So for each group, there is some kind of a specific naming convention that people actually use. So as a result, don't get confused by this. Also, there are situations like if there are 2 groups which are really isomorphic, like for example, S3 and D3, let's say, people may be using different names for different groups, even though they are isomorphic and even though the character table is identical, right? That's also another thing that you have to be careful with. But in any case, what we are going to say at the end is that this is a square table. The number of rows is equal to the number of columns. So basically, we are going to say that the number of irreducible representations is the same thing as the number of conjugacy classes, right? That's That's one relationship that we have mentioned. But there's another thing in here. There's some kind of an orthogonality relationship between these characters as well. So that's what I'm going to derive next. So first of all, let's just remember this, right? Chi mu of whatever G is equal to trace of U mu G. So I can then write this thing down as sum over I of UII mu of G. Okay, just note this. All right. So, I mean, basically the character for any element is the sum of the diagonal entries. Now, I'm going to remind you this orthogonality of matrix elements. I'm going to write down the relationship again. Somehow I memorize this, so therefore I can write down without thinking deeply about it. I can even write down while still talking. At some point, you are also going to get this ability at some point. PQ. Yeah, all right. So that's the expression. So there's a summation over G. All the other numbers, I, P, J, Q, these are not summed. Okay. But what I need to do is I need to choose P is equal to I in here, and Q is equal to J, and sum over IJ, right? But first of all, before the summation, let's just see what happens in here before the summation. So this is 1 over G. This is a sum over G. UII mu star of G. UJJ mu of G. That's equal to 1 over D mu. Delta mu nu, delta IJ, delta IJ. So on the right-hand side, I have delta ij, which is basically the square of delta ij, right? Square of delta ij. But the Kronecker delta is either 0 or 1. And these are the only numbers where their squares are equal to themselves. And so as a result, this implies that I can remove the square and I still get the same thing. Basically, if I is equal to J, I get 1 in here. If I is different than J, I get 0. So with this expression too, I'm going to get this. All right. Next, let me use a different color for that. So I'm going to do a summation over I and summation over J, which means that I also need to do this on the right-hand side. Sorry, a summation over I and a summation over J, all right? I cannot squeeze it in here. But what I'm going to do is on the left-hand side, I'm going to move that summation over I to inside, and I'm just going to do the summation over I in here. And I'm going to move the summation over J inside again, and I'm going to do the summation in here. So that's a summation over J. On the right-hand side, I have something like this. So let me try to write this carefully. So there's going to be a summation over I and a summation over J of delta ij. So this is something that you have to be careful with. First of all, just note that when you are summing over J, when I is fixed, all of these entries becomes 0 except one of them. So as a result, this whole summation is equal to 1. And then I have a summation of 1s over an index I, which means that how many indices I have, it's about d mu indices. So there's basically d mu terms in here. So that's basically 1 plus 1 plus 1. This appears d mu times. So as a result, this expression is equal to d mu. It's equal to the dimension. Or alternatively, you can think of this as like the trace of, or the sum of the entries of an identity matrix. Yeah, whatever. I mean, just think about it, right? So at the end, I'm going to get delta mu nu on the right-hand side, and on the left-hand side, I get this. This is the sum over the group elements of character of mu over the group elements. I mean, this is a summation over the group elements. So I'm basically, what I'm doing is like, I'm multiplying the character of an element corresponding to a representation with the character of the same element for a different representation, and then summing them up. This is a sum over the group elements, but I can easily convert this into a class summation. So as a result, this can be written like this. So let me say it like this. This is a summation from 1 to the number of classes. And then we have ni, character of mu I star, character of mu I. That's equal to delta mu. I think I'm going to go up to that table.
So can you wait a little bit longer there? I
yeah.
couldn't finish writing. Thank you.
Yeah, you need to finish writing. All right. Right, this is called the orthogonality of, let me say orthogonality, right? It's called the orthogonality relationship of characters. Just remember this. This was called the orthogonality of the matrix element. So this one is different now. It's the orthogonality of the characters. So in that case, I'm not interested in the matrix representations. I'm not looking at the matrix elements, but I'm just looking at the characters. And the characters does not depend on the similarity transformation that you use. So all equivalent representations have the same character.
John, thank you. Actually, I finished.
All right. Now, but you can see that, just note, right? I can use the same kind of an argument in here. So I can define vectors now. So let me call this as like vectors u mu. Define like that. Sorry about that. So I basically define these as column matrices where the entries are the square root of ni divided by the group order multiplied with the character. All right, let me show it like that. In that case, each of these expressions can be actually thought as the inner product of, or the dot product of, yeah, it's just the orthonormality relationship between u mu and u mu. I think I'm going to use this inner product expression. Okay. So this is actually an orthogonality relationship. And I can even say that this is orthonormality instead of orthogonality. But in any case, the thing that I have done above, I can do it in here. So therefore, I can say that the number of irreducible representations, which is basically equal to the number of vectors that I can define in here, number of different vectors, should be less than or equal to the dimension of this vector space, which is equal to the number of conjugacy classes. Again, at this point, I cannot show that they are indeed equal. but they are equal. So um, there is this technical part in here which is quite hard to show, the equality in there. Um, so we need to go into some kind of technical details to be able to show that this is the case actually. But it turns out that, well, there's no inequality in here. This is always equal. Okay. So as a result, because of the equality here, we also have the corresponding completeness of the characters relationship, right? So I'm just going to say it like this. This is the completeness. Let me say it like this, right? If these are actually indeed equal to each other, then we can write down the completeness of characters relationship. So this basically tells us that if I do a summation over mu of ni, there's 1 over g is also outside, character I mu complex conjugate, character j mu is equal to delta ij. And I think I can move this I to the other side. Or g divided by delta ij. Okay, so then that's the other relationship. Right. What I'm going to do now is just go back to the group and then just verify that these are indeed the case. So I'm just going to show them one by one. All right. So, but the orthogonality is the kind of the most obvious. So, and is the one that we actually use a lot. So that's the orthogonality. Orthogonality is like 1 over g times sum of I, ni, chi I mu star chi I mu is equal to delta mu. And this is the completeness. So that's 1 over g. This time the summation is over the other index. Chi I mu complex conjugate chi j mu, that's equal to delta ij divided by ni. I think I can move this order of the group to the other side as well. So let me do that. Why not? Sorry about this. This is the order of the group divided by ni delta ij, right? So in any case, the orthogonality relationship is the orthogonality between the rows. You take this row and then multiply with the corresponding entries of each row, and in each case you also multiply with the elements within with the class. This is not important if you're multiplying 2 different rows, because at the end you are going to get 0 eventually. So the order of the group is not relevant for these kind of things. But for normalization, yeah, this is something that you need, right? So I think I'm just going to check a few of these. So for example, let's say orthogonality of the first 2 rows. Okay, I mean, this is just the way that we do this calculation. We multiply this number, that number, and that number. So in the first case, identity case, each one is 1. And then for this one, yeah, I made a mistake in here. Sorry about this. So I'm going to undo all of them, right? So I'm multiplying the number and the entries and add them up, right? Number and the entries and add them up, okay? So as a result, if I'm doing this with the representations U1 and let's say U2, the products are basically 1 times 1 times 1 plus 3 times 1 times minus 1, and then 2 times 1 times 1. Add them up, you get 0. right? So this basically shows that these two rows are orthogonal to each other. Okay. Yeah, I think I don't want to continue with this, but I can easily show the other ones. So um, the sum of the squares of each column. So this is basically the normalization for the completeness. So columns gives us this completeness relationship. So when I is equal to j, what you have inside is basically the sum of the squares in here. So in the first one, you get like 1 squared plus 1 squared plus 2 squared. You get 6 in here. And on the right-hand side, you get 6 divided by 1. I think I'm going to leave that to you. So I'm not going to go over with this one. But this is one of the things that you can actually check. So basically, this character table, provided that you actually multiply with these extra numbers in here, provided that you multiply them, this character table is kind of like a unitary matrix, all right? So as a result, there are some orthogonality relationships between the rows, and there's a corresponding orthogonality relationship between the columns. And in some cases, actually, we try to find the character table. We try to find some unknown entries in the character table by using these orthogonality relationships. And it turns out that, I mean, even for complicated groups, this is actually quite helpful. So without actually finding the representation themselves, you can construct the character table. That's quite interesting, actually. Okay, so let me, well, I have to stop in here, so I cannot do anything further in here. Next Monday, we won't have anything because this is like spring break. We will take a break, but in the next one, we are going to revisit the regular representation that we have discussed earlier. The regular representation, if you remember. So the regular representation of a group was the representation by the corresponding permutation matrices, if you remember. It turns out that the regular representation contains all irreducible representations. And so as a result, by using this, we can actually show one of the fundamental relationships, right? So this is the next thing. And I don't know if I'm going to show the other relationship, the fact that this is actually a square matrix, that the number of irreducible representations is equal to the number of conjugacy classes, because this is a little bit more mathematical than the rest. Okay. I can perhaps prepare an offline video about this. I don't know, but let's finish it in here. I'm going to read your midterms at some point, eventually, but there's always this extra jobs that we always find. So I have another midterm for another class. But hopefully within the next 2 weeks, I'll be able to read them.